Hello, advanced chemistry students. This is Dr. Rogalski. We're taking a look at the final section in the Chapter 13 unit on gases, and that is gas law stoichiometry under non-standard conditions. We've already taken a look at stoichiometry and using gases in the stoichiometry unit, and in those cases we were working with conditions of STP. If you recall, we had STP conditions. We'll talk a little bit more about what they were, but hopefully you remember what they are. And in the case where we had STP, the coefficients in the balanced chemical equation represented the volume ratios for the gases. So if we had the combustion reaction, which is given below, hopefully you all remember what combustion reactions are. We have a situation where the coefficients in this balanced equation, so we have 1 here, a 2 here, a 1, another 2. Those coefficients represents the amount of the substance, and in this case, the volume of the substance. So in one case where we would have 1 mole, it's actually more convenient to talk about the volume. So we have 1 volume. So 1 volume of methane would react to 2 volumes of oxygen to produce 1 volume's worth of carbon dioxide and 2 volumes of water vapor. So this is an important idea to keep in mind. And we know how that works in STP. We know something about the molar volume relationship, and we'll see that in a bit. What we're doing in this chapter, however, we'll be working at non-STP conditions, and that makes this a more complex problem. So again, in the first example we're taking a look at, this problem is example 7 on page 461. The question is, what volume of oxygen gas is needed for the complete combustion of 4 liters of propane? So we have 4 liters of propane. Assume, and again, they're asking us to find the volume of oxygen gas necessary, assuming that temperature and pressure remain constant. So that's an important assumption right here. And basically, this turns out to be a volume to volume problem. Well, the first thing we have to do is write the balanced equation for propane. So we have C3H8, propane gas. It's combusting with oxygen gas. And I'm balancing it as I go along. Produces 3 carbon dioxides plus 4 water vapor gases. So the coefficients are 1, 5, 3, and 4. And we can think of these all in terms of volumes, in other words, liters. So if we have 4.00 liters of propane, and the question asks us how much oxygen gas are we going to use. We're again going to use essentially what we know as the molar ratio, only we're taking the ratio of volumes. We know that 1 volume of C3H8, or liters of that, would require 5 times the volume of oxygen gas, or 4 times 5 is 20 liters of O2 gas. And again, if this is a combustion reaction, and with combustion reactions, remember that if you're using hydrocarbon and oxygen gas, you will always produce as products carbon dioxide and water. Now, in starting these kinds of problems, you know that we know that a balanced chemical equation allows you to find ratios for the mole for only moles and gas volumes, but not for masses. And why is that? Because molar masses vary. So what the mass is has always had to be converted into moles because molar masses differ from one substance to another. So if you're given a problem with masses, they must all be converted to moles or volumes before you can use them part of a ratio. This is a very important idea. And you'll see how this plays out in the problems ahead. Now, one of the first examples we'll look at is on page 462 of your textbook, example number 8. We are looking at the Haber process, whereby nitrogen and hydrogen gases are reacted to produce ammonia. In this case, we are going to assume that hydrogen is in excess, and we will look at the conditions under which the reaction is going to take place. Just a side note, the Haber process is very important in production of ammonia because ammonia is then taken on to produce fertilizers. This is a very big deal in the early 20th century. Okay, back to chemistry. Let's collect our data on the side here. So volume of nitrogen is given at 5 liters. The pressure, so 5 liters for volume, pressure is 3 atmospheres, and the temperature is equal to 298 Kelvin. The question is ultimately how much ammonia will make in terms of grams. Okay. So first question you might ask yourself is this reaction taking place at STP? Well, the temperature is 298 Kelvin. That's not standard temperature, and the pressure is 1 atmosphere, 3 atmospheres, which is also not standard pressure, so the answer is no. So that makes this a longer problem. We are given that we have 5 liters of nitrogen, and eventually we want to get to how many grams of ammonia. So the thing we would want to do now is convert the liters of nitrogen into liters of ammonia, and that's a volume to volume problem. So first, volume to volume. We can do this because all of these things are going to occur in the same tank. So we have 5 liters of nitrogen gas. We look at what we would normally think of as the molar ratio. In this case, it's the volume ratio. 1 mole of nitrogen up here produces 2 moles of ammonia, so 1 volume's worth of nitrogen equals 2 volumes of ammonia, and that means we are producing 10 liters of ammonia gas. Well, that's fine. We know how many liters of ammonia we're going to make. The question is asking how many grams will that be. So the thing now is we can use our Pivnerd equation, our ideal gas law. So use PV equals nRT to find N, which will be the moles of ammonia. And then from there, we'll go ahead and convert moles back to grams using the molar mass. Okay, so let's start. We have PV equals nRT. We are going to solve for N. That'll be the number of moles of ammonia. We have 3 atmospheres. So N is going to be equal to PV over RT, which then is equal to 3 atmospheres. 10 liters of ammonia. That is the number we got from doing a volume to volume problem. We have to pick a value for R, and the temperature was given at 298 Kelvin. So we have to pick the value for R being the universal gas constant that has units consistent with the units of pressure in our Pivnerd equation. And that happens to be the value 0.0821 liter atmosphere mole Kelvin. Okay, so just do a quick check on your units. Atmospheres cancel, liters cancel, Kelvin cancels. I'm ending up with moles, which is what I'm looking for. So if you go ahead and do the calculations, you get 1.23 moles of ammonia gas. The question then is, how many grams would that be? Well, we have to calculate the molar mass for ammonia. We've been doing this for a long time now. So basically that should be N times 1 times 14, 14.00, H times 3 times 1.018 equals whatever that is. Basically, comes out to be 7.04 grams per mole of ammonia for its molar mass. All right, we're going to take 1.23 moles of ammonia and convert that to grams. So 1 mole of ammonia has 17.04 grams of ammonia. And if you go ahead and do the units and the math, you come out with 21.0 grams of ammonia. So if we go way back to the beginning, if we have 5 liters of nitrogen gas reacts completely with an excess of hydrogen, we will eventually produce 21.0 grams of ammonia. Okay, and that's how the first problem works. If you want to see this worked out again or in a different way, you can look at your textbook. And that's it for the Haber process to produce ammonia. Hope that was helpful. Okay, now we've already learned this. We're looking at what standard conditions are. We did this back in the stoichiometry unit. Standard temperature is 273 degrees Kelvin or 0.00 degrees Celsius. Standard pressure is 1.00 atmospheres or 101.3 kilopascals. If all these things are true, then the standard molar volume is 22.4 liters per 1 mole. So this is called the standard molar volume. And this is only holds true if you're at conditions of STP. So many reactions involving gases will occur under non-standard pressure and temperature. In fact, most of the ones we do in the lab are occurring at non-STP conditions. The lab is about 1 atmosphere, but usually the temperature is more room temperature, which is more around 20 degrees C than 0 degrees C. So again, when we have this kind of problem, the conversion of moles to reactant to moles of product when volumes are involved must take place under conditions of STP. And the thing is, if the gases involved are given in moles or grams, then there's not so much you have to do, especially in moles. And we'll take a look at these kinds of problems some more. Okay, let's take a look at one of these problems where we are operating under non-standard conditions, and we need to find out how much gas is going to be required for a reaction. So the question says, what volume of chlorine gas at 24 degrees C, 99.2 kilopascals would be required to react with 2.51 grams of silver according to the equation below. So 2 silvers plus chlorine produces 2 silver chlorides. That equation is balanced. First thing is to ask yourself, is this at standard temperature and pressure? The answer is no. So we're going to have to use the usual stoichiometry combined with the ideal gas law to find the volume of the gas. Well, one of the first things we know is that we have 2.51 grams of silver. That's one reactant. And we can relate that amount of silver to chlorine, the amount of chlorine necessary in terms of moles. And once we find the moles of chlorine, we can use the ideal gas law to convert it to a volume. So we're going to start with the silver. So 2.51 grams of silver. You'll have to look, in order to convert it to moles, you're going to have to look up the molar mass of silver. It's 107.87 grams per mole of silver. And for every 2 moles of silver, we will require 1 mole of chlorine gas. So again, this is our molar ratio. If we can take a look at our units, moles of silver, we will come up with the number. We'll come up with a number of 0.0116 moles of chlorine gas, or we could round that to 0.012 moles of Cl2, given that we are operating with 3 sig figs in this amount of silver. Actually, this is 2 sig figs, so we probably actually want to carry forth using the 0.0116 moles of chlorine. And that will correspond to N in the ideal gas law. All right, so actually in my calculations I've worked out N is going to be 0.12. Probably could have carried the extra decimal place. So now we're going to use the ideal gas law. So PV equals nRT. And we're looking for the volume of the chlorine gas that's going to be required. So we'll solve for V. V is now equal to nRT over P. And now we will just substitute that in. We're going to figure out, let's see, the pressure was given in kilopascals. So we're going to use a value of R, which is 8.314 liter kilopascals mole Kelvin times T, which was 297 Kelvin, all over the pressure, which was given as 99.2 kilopascals. Now go ahead, do the unit check, make sure this is set up correctly. So we have moles will cancel, kilopascals cancel, kelvins cancel, and we're left with liters up here. And when liters is a correct unit for volume, so in the end we will get 2.98787 times 10 to the minus 1 liters, or 0.2987 liters. And again, we probably should be carrying through, I would say, 3 significant digits. So V equals 0.299 liters of Cl2 gas. That's going to be the amount needed to react with silver. Okay, and that's how these kinds of problems work. You're usually going to do some stoichiometry and then the ideal gas law, or the ideal gas law, then some stoichiometry. And that's how it's done. Hopefully this was helpful. Okay, in this problem, we are asked to find the mass of mercury to chloride, which will react with 0.567 liters of ammonia, 27 degrees C, 102.7 kilopascals, according to the equation given below. Need an arrow. So first of all, we ask our question, is this system at STP? First, the answer is no. This is not, at STP, this would be 0, and this would be 101.3. So what we're going to do then is to take the volume of ammonia that's being used and eventually convert that into moles of ammonia. So in this case, we're doing stoichiometry first. Once we find the moles of ammonia, we can plug it into the ideal gas law to determine the moles of we're going to find the, we'll take the 0.567 liters of ammonia, use the ideal gas law to find the moles of ammonia, and then go from there to find the grams of the mercury chloride. Okay, we're going to do this then by starting with the ideal gas law again. PV equals nRT. This time we know we have the volume of the gas. We'd like to know how many moles of that gas is. So we'll be rearranging it. N equals PV over RT. We are going to then substitute in the pressure was 102.7 kilopascals. The volume was 0.567 liters of 6.567 liters of ammonia. We choose the value of R with the correct units. That would be 8.314 liters kilopascals mole Kelvin. And the temperature is 27 plus 273 or 300 Kelvin. If we go ahead and do the unit check quick to make sure everything's in order. We end up with moles, which is what we're looking for. So this will be the moles of ammonia. The number comes out to be 2.33 times 10 to the minus 2 moles of NH3. Well, now we've taken the volume of NH3 or ammonia, converted it to moles using the ideal gas law. Now we have to do stoichiometry to relate it to the amount of mercury chloride we're going to need. So 2.33 times 10 to the minus 2 moles of ammonia. We have 2 moles, back to our balanced equation, 2 moles of ammonia react with 1 mole of mercury chloride. And since we want it in terms of grams, we have to calculate the molar mass of mercury to chloride. So you know how to do that. 1 mole of mercury to chloride, 271 grams of mercury chloride. And that ultimately comes out to be 3.16 grams of HgCl2. 3 sig figs will work. And so that's the answer for that problem. So in this case, you saw that we needed to use the ideal gas law first because one of our reactants was given in terms of a volume. We needed to convert it to moles. And then we took moles, used a molar ratio to find, and then the molar mass to find the grams. So most of these problems work in the same way. You do some stoichiometry and then the ideal gas law or vice versa. Hope that will help. Okay, so this is another kind of problem. This is more practice. And there is a worksheet in Schoology that has a number of these problems along with their answers. So in this case, we're going to start with 25.04 grams of potassium chlorate. It is decomposed. What volume in liters of oxygen gas is produced if the gas is collected at 738.8 millimeters of mercury, 34.0 degrees C? Well, the very first thing we have to do is write the balanced equation. So potassium chlorate is KClO3, solid. We're decomposing it with heat, and that produces KCl, potassium chloride, solid, plus O2 gas. If we balance, okay, once we write the balanced equation, we see that 25.04 grams of potassium chlorate are decomposed, and the question is what volume of oxygen gas is produced. The pressure is 38.8 millimeters of mercury. You can convert that into atmospheres, we can do that. So 760 millimeters of mercury is 1.00 atmospheres, and that comes out to be 0.9721 atmospheres. The temperature is given at 34.0 degrees C, must be in Kelvin, so add 273, and that gives a temperature of 307 Kelvin. Okay, so we've got some of our variables converted into the proper units, and we'll continue on the next page. Well, we have 25.04 grams of KClO3 potassium chlorate, and we need to convert that to moles. So the molar, you have to figure out the molar mass, which is 123 grams per mole of KClO3. And we eventually want to know how many moles of O2 are going to be made. So we might as well take the molar ratio and go for it all in one step. So we see that 2 moles of KClO3 produce 3 moles of O2. Check the units, grams of potassium chlorate, moles potassium chlorate. We're left with moles of O2. That's what we're looking for. So that will come out to be 0.306 moles of O2 gas. We are looking for the volume of that much oxygen gas. So we are not at STP conditions, so we're going to use PIBNERT. So PV equals nRT. We are looking for the volume, so V will be equal to nRT over P. And now we substitute in. N is the number of moles of oxygen gas, 0.306 moles of O2. R, because we've converted to atmospheres, can be 0.00821 liter atmosphere mole Kelvin. Temperature we converted to Kelvin, so 307 K all over P. Pressure we converted to 0.9721 atmospheres. And now the volume then, check for all your units. Moles cancel with moles. Atmospheres cancel with atmospheres. Kelvin with Kelvin. We're left with liters. And volume comes out to be 7.933 liters of O2. Looking at the pieces of data, I would say that 3 sig figs will work out. So the answer is going to be 7.93 liters of O2. Okay, That's another one of these practice problems. I have one more to do, and then hopefully that's good enough and you can practice some on your own. This one here doesn't really fit into the scheme of things. It's really a dimensional analysis problem. I'm going to go ahead and just show you how you lay it out, but we're not going to go through it. It doesn't really fit in here too well. Breath per minute, 60 minutes per hour, 24 hours per day, 0.505 liters per breath, and that would come out to be 10908 liters of air. From that, you can go ahead and finish it up. Again, this one's not really one that fits into this scheme of stoichiometry. It's simply dimensional analysis. Okay, now this is the last problem I'm going to work through. Like I mentioned before, there's more problems on Schoology in the form of different worksheets with answer keys. In this case, we have 31.24 grams of sodium chloride reacting with excess fluorine gas in a single displacement reaction. What volume of chlorine gas is produced if the gas is collected at 28.75 inches of mercury and 29.0 degrees C? Taking a quick look, you can see that it's not at STP. And the next thing we really need to do is write the balanced chemical equation. So 2 sodium chlorides plus F2, sodium chloride's a solid, fluorine's a gas, single displacement, so the fluorine knocks out the chlorine to produce chlorine gas, plus 2 sodium fluoride, and that's a solid. So that's our balanced chemical equation. Keep in mind, chlorine gas, fluorine gas are all diatomics. That makes a big difference. So we're starting with sodium chloride. It's the excess reactant. It's the limiting reactant. The fluorine is in excess. And so we need to convert 31.24 grams of sodium chloride into moles. So we'll start with that. 31.24 grams of NaCl. I have to look up the molar mass or calculate it, the molar mass of sodium chloride, which is 58 grams of NaCl per mole. So a lot of rounding here, so you may actually want to look this up with some more decimal places. 1 mole of NaCl. 2 moles of NaCl produce 1 mole of chlorine gas. That's our product. So this is again is stoichiometry using the molar ratio to relate the two. And if you go through, check your units, you will and do the math, you come out with 0.269 moles of chlorine gas. Okay, so that is going to be the N in the ideal gas law. Okay, so we are going to write the ideal gas law out. PV equals nRT. And again, we're looking for the volume of the chlorine gas, so we can solve for volume. So V equals nRT over P. V equals nRT over P. And go ahead and make all the appropriate substitutions. So this will be N is going to be the moles of chlorine gas. So that'll be 0.269 moles. R, we're going to convert millimeters of or inches of mercury into atmosphere. So we're going to be using the R, which is 0.0821 liter atmosphere mole Kelvin. And temperature, again, would be 29 plus 273, or 302 Kelvin. And the pressure we're going to convert, I'll write the conversion here since we haven't done it anywhere else, but 28.75 inches of mercury. And we're going to convert it to atmosphere, so that's 29.92 inches of mercury is 1.00 atmospheres. So this number for pressure comes out to be 0.961 atmospheres. Okay. So again, go ahead, cancel your units. We're looking for volume, so moles of chlorine cancel, moles here cancel, atmospheres cancel, Kelvin cancels, inches of mercury. And what are we left with? We are left with liters after we do the cancellations. So volume comes out to be 6.94 liters of Cl2 gas. And that's the answer. So as you can see again, first we did some stoichiometry and then we did the ideal gas law. So in doing gas law stoichiometry under non-standard conditions, you can expect to do some stoichiometry and some work with the ideal gas law. Okay, that's it. Practice some more problems off the Schoology pages, and I hope that helps.